I guess that's what happens when you're the baby and you've got two older sisters and you wrestle around a lot. But okay, so in chapter 4, we spent a great deal of time talking about applications of derivatives and how we can use derivatives to inform us about different aspects that functions have. Okay. Today we're going to discuss two theorems, Rolle's theorem and mean value theorem. Both are very important. The latter, however, is the one that I put the star by because you will use mean value theorem to justify things on the AP exam. So that one is what I would call a note card worthy theorem. Hey, how are you? That's great. Okay, so mean value theorem is a note card worthy theorem, definitely an important one. But first we're going to talk about Rolle's theorem, which is kind of like a little offshoot, a precursor to mean value theorem. Okay, so, sorry, I'm going to take attendance real quick while we do this. Rolle's theorem says the following. If you have a function that is continuous on the closed interval and differentiable on an open interval a to b, then if you also have that f of a equals 0, so your output of your endpoint at a is equal to 0, and then your output at your endpoint at b is also 0, then there has to be at least one value c in that open interval from a to b such that f prime of c is equal to 0. Yeah, what attendance are they talking about? Everything is taken. Strange. Okay. All right, so you can very clearly see this on the graph as well too, and I think this should make sense just by thinking about it. I've got a continuous function that's defined on a closed interval. If my endpoints are equal to each other, they both have an output of 0. If your function goes up, it's got to go down, so you're going to have a relative extrema or an absolute extrema somewhere on that interval. Okay. However, we can see that in an instance like this, I can have that it's not going to happen as well. So in this function, definitely continuous. Is this a differentiable function? No, because I have a sharp turn at c. So because of that, the value of my derivative is not equal to 0 at this point. My value doesn't exist. However, since my function was not differentiable on that open interval, then that's why Rolle's theorem fails in this case. Now, you can also have more than one critical point as well too. So if I draw... I don't know, just make a little sketch. And let's say we have something that looks like this. And let's say the endpoints are of our interval here, A and B. We can see that there are two values such that we would have a derivative of 0 on that interval. So we've got one in that first loop right there, somewhere around here, c sub 1, and then we've got another one, c sub 2 right there as well too. Okay, so two values such that the slope of our tangent line is going to be equal to 0. Okay? All right, so here's how this typically looks. There's three things that we need to check to make sure Rolle's theorem applies. First, needs to be continuous on the closed interval. That's thing 1. Thing 2 is it's got to be differentiable on an open interval. And then my third thing is that my endpoints have an output of 0. Okay? Now, your textbook specifically talks about Rolle's theorem as having your inputs of an output of 0. But truthfully, the picture that I've shown here doesn't have endpoints with an output of 0. Okay? As long as your endpoints are equal to each other, Rolle's theorem still applies. So for example, if you look in this picture, your output at A is D, and your output at B is also D. And Rolle's theorem is still going to apply. If I shift that down to the x-axis, you can see that then it hits exactly Rolle's theorem as your textbook says. But okay, so again, process is this. Make sure those three things apply. If they do, take your derivative side equal to 0 and find your x values. Simple as that. So let's do that. We've got y equals sine of x on the interval from 0 to 2 pi. We want to make sure that the hypotheses of Rolle's theorem are satisfied, and then if so, we want to find the c that's guaranteed by Rolle's theorem. All right, so we got to check for continuity and differentiability, and then also our endpoints. Okay, sine of x, y equals sine of x. Is that a continuous function? Yeah, absolutely, right? Think about the graph of sine of x. Just oscillates back and forth between -1 and 1. No breaks, holes, gaps, vertical asymptotes, vertical tangent lines, anything like that. So we would say that y is continuous on my closed interval from 0 to 2 pi. Yay. Is it differentiable? What's the derivative of sine? Which is also continuous on that open interval, right? So we would say that y is differentiable on the open interval from a to b. So we're cool there. All right, let's check the outputs of our endpoints. If I make this like function notation, I'm going to do y of 0 and then check y of 2 pi and see what we get. Hopefully it should be 0. All right, so if I plug in 0, what's sine of 0? 0. What's sine of 2 pi? Hooray. So my outputs agree, and they both equal 0. All right, because of that, Rolle's theorem should apply to this function on that interval. So now I want to take my derivative and set it equal to 0. So y prime is equal to, well, we already talked about this, but the derivative of y is just going to be cosine of x. And so I want to set that equal to 0. So I need to employ the use of the unit circle in order to find where those values are 0. What x values make cosine equal 0? Cool. Thankfully, we're working on that closed interval, so I don't need to mess with k or anything like that. All right, so pi over 2 and 3 pi over 2 are going to be my values. And are they both on the interval? Hooray! Cool. So I would say that I should say c equals instead of x equals, but I forgot to use that notation. Either way is fine. I wouldn't really care either way. But again, we're finding our c values, so we just did pi over 2 and 3 pi over 2. It doesn't ask for our outputs at those c values. It could, but it doesn't. So I'm not going to bother plugging those in and checking those values. Okay? All right, super. All right, let's look at this one. So now we've got a rational function defined on a closed interval. So we want to make sure the, same thing, make sure the hypotheses of Rolle's theorem are satisfied. And if so, find all the c values guaranteed by Rolle's theorem. Ooh, rational function has some potential to be discontinuous, right? I mean, I have a denominator here, right? So is my function continuous? Yes, on what interval? The one I'm given, which is the one I care about, right? What x value would make my function discontinuous? -2. It's outside my interval, though, so that's okay. So because of that, I'd say that y is continuous on my closed interval. All right. Is it differentiable? Sometimes it's not immediately obvious, so you got to do a little bit of thought. If I take the derivative of this, what will that require? Quotient rule. So low d high minus high d low, and then the part we care about for this part, which is over low squared, right? So low is x plus 2. So over low squared would be quantity x plus 2 quantity squared. What values would make that not differentiable? Also -2, right? Falls outside my interval, so I'm cool. So I would say y is differentiable at, or I should not at, but on my interval, open interval from -1 to 3. And if you weren't able to reason through that right away, then take the derivative and look at what you get with the derivative, and then circle that part to that back. Circle back to that part, sorry. So take the derivative if you aren't sure whether it is differentiable or not, and then circle back to, well, is it differentiable? Okay, which we're going to do that in a second. So, all right, now I need to check to see that, I need to check my endpoints. I need to check y of -1 and then y of 3. Now, this was the example I had to fix.
I have a question about like the differentiable one.
Yeah.
Wait, so why is it open and like on the other one you put like AB instead of like the numbers? Like,
Oh, did I?
Yeah. Like is it?
I don't know why I did that. I mean, I should have just did 0 to 2 pi.
Oh, okay.
AB is understood. with, because that's like this interval. But honestly, I should have put 0 to 2 pi in this case since I have a specific example. So that's my bad. It is continuous on the closed, though. It's got to be continuous on the closed. It has to take values at the endpoints. But then since differentiability is born out of a limit, I just have to make sure the limit exists from the left and to the right. So that's why it's differentiable on the open but continuous on the closed. Okay? All right. Let's check my endpoints. This was the example I had to correct. Your files all say this same function, right? X squared minus 2x minus 3. It doesn't say x squared minus 3x minus 3, does it? That's the mistake that I made before, but I had to fix it. So, all right, we're good. Just want to make sure that upload worked fine. Okay, so if I plug in -1, not with a crayon. Oh, let's try a thin crayon, see if we like that. -1 squared minus 2 times -1 minus 3 over -1 plus 2. Up top, what do you get? Oh, thank God. And then over 1, so then that's going to be equal to 0. Yay. And then let's plug in 3. So 3 squared minus 2 times 3 minus 3 over 3 plus 2. Same deal. What do you get up top?
0.
Nice. So 0 over 5, which gives me 0. Great. That was the other condition that needed to be met. Now, I will take my derivative, and I will set it equal to 0. So y prime is equal to, all right, so low, d high, minus high, d low. So x squared minus 2x minus 3. And then the derivative at the bottom is 1, so I'm not going to be pressed about that. So over x plus 2 quantity squared. All right. Let's simplify. I get 2x squared minus 2x plus 4x, and then minus 4, and then minus x squared plus 2x, and then minus 3? No, plus 3, sorry. Sorry. Over x plus 2 quantity squared. And then we simplify. So got a common factor with x squared, and then positive 2x plus 2x is plus 4x, and then negative 4 plus 3 is minus 1 over x plus 2 squared. Ah, fudge. What happens with the top? I can't factor it. So I need to use quadratic formula. So let's do that. Because I do have to set it equal to 0. Okay, so negative 4 plus or minus square root of 4 squared minus 4 times 1 times negative 1 all over 2 times 1, which is 2. Negative 4 plus or minus square root of, all right, 16 plus 4 over 2. Okay, that's actually not that bad. So then negative 4 plus or minus square root of 20 over 2. Which I can simplify that, right? What is square root of 20 simplified to? Very good. And then I can reduce a common factor of 2 betwixt the top and bottom. So negative 2 plus or minus square root of 5. Okay, so those are my x values, or I should say my c values, right? That's what I'm looking for. Let's see, since I have 2 of them, let's double check that they are values that I want. Meaning, do they fall within my interval? So square root of 5 is like, oh man, was it like 2.23, I think, something like that? Okay, so if I do negative 2 plus 2.23, then that's going to give me a slightly positive number. Is that between negative 1 and 3? Yeah, okay, so then that's good. And then let's check my other one. Negative 2 minus 2.23 would be like negative 4.43 outside of my interval. I don't want it, right? So my only solution is the one that I circled. Okay, when working with intervals, always go back and check and make sure that your solutions fall within that interval. All right, questions there? Okay, all right. We've got f of x equals absolute value of x minus 1, operating on the interval from -1 to 1. Verify if the hypotheses of Rolle's theorem are satisfied, and if so, find all the c values guaranteed by Rolle's theorem. Okay, absolute value of x minus 1. Is it continuous? Yes, because it's just a combination of continuous functions, right? X is continuous, absolute value is continuous. Subtracting 1 is not going to make a difference there. So we would say that f of x is continuous on closed interval -1 to 1. Is it differentiable? No, you guys know a decent amount about absolute value. What is going to happen? A sharp turn. Where at? 0, because that's what makes the inside of the absolute value equal 0. So I would have a sharp turn at 0. Now, if I did want to show the work for that, I would have to define this as a piecewise function. So negative x minus 1 and then x minus 1. This would be when x is greater than or equal to 0. This would be x is less than 0. We know that's a continuous function. However, my derivative would look like -1 up top, 1 in the bottom, x is less than 0, x is greater than or equal to 0. First of all, there's no values that would make your derivative equal 0, right? Your outputs are just -1 and 1. It's never going to equal 0. Second of all, we would know that our limit as x approaches 0 from the left of f prime of x does not equal our limit as x approaches 0 from the right of f prime of x. Therefore, f is not differentiable at x equals 0. This song's a banger. Rasika, did you play Paramore?
No, I don't do it.
You don't do it second period? Okay.
I do like Paramore.
I love Paramore. Haley Williams is a goddess. All right. Let's do mean value theorem.
What time are we doing this test?
Yeah, because you're going to dip out a bit.
Well, I told them that I wouldn't do it if you want to do it in class. I told them that I don't want to do it.
It's going to be at the end. And you might have enough time, though, Rasika.
I don't think so. How much time are you doing this?
Depends when I finish the lecture, but it'll be like... I know. It'll be more than that.
Really?
Yeah. Yeah.
Oh my god. It's the limit for...
Thank Daisy and her
when you're
dislocated
checking
elbow.
this reversible, do you check the limit? Why? F prime of x or limit?
F prime. Because I'm determining if my derivative is differentiable or not.
Okay.
Or I'm determining if my derivative is continuous or not. So that's why it's f prime of x. Okay. All right, here we go. Mean value theorem. Okay, so there is a star next to mean value theorem because it is an important one. Okay, this is one that you will use to justify things on the AP exam. Okay. Now there is a mean value theorem for derivatives, which is what this is, and then there's also a mean value theorem for integrals as well too, which we'll get to a little later in the course once we start getting into chapter 5 stuff. Okay. Now, the preambles are the same as Rolle's theorem. So, continuous function on a closed interval, differentiable function on an open interval. If that's the case, this is the only two things we need to check. If that's the case, then there has to be some value c in that open interval a to b, such that the derivative at c is equal to f of b minus f of a over b minus a. What is this right here? What is that? I heard it. Average rate of change or slope, right? Slope between the endpoints of your intervals, but that also tells you your average rate of change. What is this right here? Instantaneous rate of change or derivative at c, right? So a couple ways you can think about this. There's two offshoots of mean value theorem, which are so very important. The first is that the instantaneous rate of change is equal to the average rate of change at that value c. Okay, that's hugely important. Okay, And that's the part that you'll use to justify some of your answers on the AP exam, is that your instantaneous rate of change is equal to your average rate of change. The other part that's important, which we kind of mentioned as well too, f prime of c, giving you your instantaneous rate of change, is your slope of your tangent line. And then that difference quotient, f of b minus f of a over b minus a, is your slope of your secant line. So at some point, the slope of your secant line between your endpoints is equal to the slope of a tangent line at a value c. I don't know, man. Teaching with a soundtrack. I should just use this time to breathe. That's what I should do. All right, so this graph is also very important as well too, because it talks about like, this is the visual representation of that big important concept that I just taught you. And you'll see that like this graph looks fairly similar to the graph that I showed you for Rolle's theorem. It's just tilted a little bit. Yeah, tilted towers. So like you'll see that the outputs at A and B, they don't equal each other, but that's okay. The slope between those points is, whatever this value is given here. You'll see that there's some value C such that if you take the slope of your tangent line at that point, it should be equal to the same thing, okay? Now, side note, this is the same thing that Rolle's theorem is saying, because if I draw a graph, and let's say my outputs aren't 0, it doesn't matter. Let's just say that my outputs are the same. What is my average rate of change between these outputs? It's 0, right? If I find the slope of my secant line between those points, it's going to be 0. Well, isn't it plain that there is also a value that has that same instantaneous rate of change as well too? Like Rolle's theorem has the same upshot as mean value theorem. Mean value theorem is just more general because it can be a slope of something other than 0. Rolle's theorem, the slope has to be 0. Mean value theorem is just whatever your average rate of change is. Okay? All right, that's the important part. Cool, now let's do a myriad of examples with that. All right, so given y equals x cubed over 4 plus 1 on the closed interval from 0 to 2, verify the hypotheses of mean value theorem are satisfied, and find all c guaranteed by that mean value theorem. All right, there's only two things to check, and thankfully we have a polynomial. Is y continuous? Yeah, it's continuous everywhere, especially on our interval. So y is continuous. Should be a check mark, by the way. That's what that symbol is supposed to be. On my closed interval from 0 to 2, a to b. Is it differentiable? Yeah, it's a polynomial. So y is differentiable. Spell it out one time. On our open interval from 0 to 2. I almost wrote a to b again. All right. So then because of that, let us now take our derivative. That's all I need to do. However, I need to take my derivative, and instead of setting it equal to 0 this time, what are we going to set our derivative equal to? The slope, okay? Now, you can start by finding your slope if you want to, or you can do your derivative first. I know I wrote y prime here, but I'm actually going to stop the train here, and I'm going to find what my slope is. So let's do my slope of my secant line, which would be, use function notation here, y of 2 minus y of 0 over 2 minus 0. All right, so if I plug in 2 cubed is 8. 8 divided by 4 is going to give us 2. And then 2 plus 1 is going to give us 3. And then y of 0. So if I plug in 0, what do I get? 1. Cool. And then what do I get in the bottom? 2. So 2 over 2 gives me? Cool. Good. All right. So then I'm going to set my derivative equal to that value of 1. Okay? All right. So I take my derivative, 3/4 x squared. And then I'm going to set that equal to 1. All right. So when I do that, let's multiply both sides by 4/3. X squared equals 4/3. Take the square root. So I get plus or minus square root of 4 over 3. However, we should get that in proper form. Plus or minus 2 over square root of 3, which is plus or minus 2 square root of 3 over 3. You guys still locked in on this lecture with me? Okay. All right. Now, are both those values in my interval? No. The negative one is not, right? So my only solution would be 2 square root of 3 over 3. I wrote x equals. I regret that, though. I wish I would have written c equals. I don't know why I keep doing that. Doesn't really matter, but. All right. Questions there? All right. Super. All right. Another one. Let's verify that the hypotheses of mean value theorem are satisfied. And if so, we're going to find all the values of C guaranteed by the mean value theorem. Okay, y equals 2x to the 1/3. Is it continuous? It is indeed continuous. Whoa. Is it differentiable? Maybe it's not immediately obvious. Should we take the derivative and find out? We're going to do it. We're going to take the derivative of 2x to the 1/3. And then we're going to circle back to what Max said. 1/3 comes out, multiplies the 2. So 2/3 x to the negative 2/3, which gives me 2 over 3x to the 2/3. Max, is it differentiable? No. Why not? Yeah, if you plug in 0 in your derivative, it's going to be undefined. So because of that, it is indeed not differentiable. Good. So y is not differentiable on my open interval from -1 to 2. All right, cool. So because of that, we would say, therefore, mean value theorem does not apply. All right. Let's do some trig. Yay! So y f of x equals tangent of x on the interval from negative pi over 4 to pi over 4. Oh, I didn't put a comma in there. Dang it, dude.
I think that's okay.
No.
We can see it. No, we all have to download it.
Yeah.
I love that it's just like coming.
Look at that code. Doesn't that look fun?
Did you write that?
Mm-hmm.
Why do you not?
I've done it a couple times throughout the course of college and stuff like that. Just so I can get that bracket to look just right.
Why can't you just like?
Because, I don't know. Because you're worth it, Sophie. That's why.
I feel like
You guys are worth it. Plus, I like my documents looking nice and clean. And then if I put the effort in this year, then I don't have to do it ever again. And it's actually not that bad. How long does it take me to make? Let's see. I made this last night in an hour and a half, something like that.
And playing with the background, or are you just like?
Oh, music directly injected into my earballs
Are you gonna
the whole
play
time.
these videos for all your other classes instead of like teaching like live?
Oh, heck no. No, I'm teaching live. I'm teaching live. Nope, we're doing it live. I find that it's very efficient to do that with the video, but I just feel like, and not a knock against anyone that does, I just, that would take away my favorite part of teaching, honestly. So, just teaching you guys, so.
Yeah, I feel like in 10 years you'll use these videos. You'll be over it.
Maybe. Yeah, the spark of my life will be gone. And Anyway, okay. Okay, hey. Is our function continuous on this closed interval? Yeah, I think so, right? Let's have a conversation about it. So, tangent's a sneaky fraction, right? Sine of x over cosine. Okay. Well, so let's verify. Where does cosine equal 0? Yeah, pi over 2 and 3 pi over 2. So we're good, right? Because those fall outside of our interval. We're operating from negative pi over 4 to pi over 4. So we're good. We're fine. Okay, so because of that, f is continuous on our closed interval from...
Those are 2 little points.
She
said it was a star.
I was asking Tessa, I'm like, is that a star up there?
It's supposed to be a graph. It's supposed to be a graph, yeah. Is it differentiable? Let's have a conversation about it. So f prime of x, what's the derivative of tangent? Nope.
Secant squared x.
Oh, no, it's not automatic yet. It's got to be automatic. Secant squared.
I'm sorry, everybody.
It's okay. If I turn that into a fraction, what is it?
1 over cosine squared x.
Yes. Which has the same discontinuities as sine over cosine. Do we agree? Even though it's squared, the values that make it 0 are going to be the same for the top and the bottom. Okay, so because of that, I can also say that f is differentiable on my open interval. All right, negative pi over 4 to pi over 4. Okay, so then now I need to find my slope, my average rate of change, and then I want to find my derivative and set it equal to my average rate of change. So I'll go off to the side, slope of my secant line. All right, so I want f of pi over 4 minus f of negative pi over 4. Sorry, those both look like negatives, you know? And then over pi over 4 minus negative pi over 4. Okay. If I plug pi over 4 into my original function, so don't lose sight of what part you need to plug it into. What's tangent of pi over 4? 1, right? Nice, very good. Yep. And then minus, what's tangent of negative pi over 4? Okay, so 1 minus negative 1 over, yeah, pi over 4 minus negative pi over 4 would be pi over 4 plus pi over 4, which is 2 pi over 4, which is pi over 2. Good. So then I combine my numerator, and I would get 2 over pi over 2, maybe, 2 over pi over 2, which gives me 4 over pi. That's kind of a problem, because it's not necessarily a nice number. Like 4 over pi is not something that we work with on the unit circle. So, okay, all right, well, we'll deal with it. All right, so then now I need to take my derivative, and then I need to set it equal to 4 over pi. So f prime of c, I'm going to do it this time. I'm going to use the letter c. We already said that the derivative is equal to secant squared c. Okay? And we want to set that equal to 4 over pi. And I want to solve for my values for c. If you would have used the x instead of c, it doesn't matter. But, you know, notation-wise, we're finding c, so I'm going to do that this time. All right? What do you guys want to do?
I don't know.
Okay. I'm going to get c by itself. Got to solve for c. What do you think? Oh, we're going to use that calculator at some point. Believe that. But we got to do a couple steps first before we can get to Calculatorville. It's been a minute since you guys solved trig equations like this, but you're capable. I believe in you.
Square root.
Okay, so then secant c equals plus or minus square root of 4 over pi. So secant c equals plus or minus 2 over square root of pi. Okay, now what? I like that. So 1 over cosine equals plus or minus 2 over square root of pi. But I don't like that it's 1 over cosine. So what can I do? I could take my reciprocal, right? Let's flip everything around. So cosine of c equals plus or minus. Now I have square root of pi living up top divided by 2. You said what? Yeah, it does look prettier. So now what I need to do is I need to find what c is, but I have to think like, okay, where on the unit circle am I going to have an output for cosine of square root of pi over 2? I don't know. I can't answer that question. I need to use what? A calculator, right? Now when I use my calculator, what do I use? Inverse cosine, good. So I would do that my c value is equal to cosine inverse of square root of pi over 2. And then I would also have to have a separate solution for cosine inverse of negative square root of pi over 2. Desmos. I had it in there from last period. All right, so cosine inverse of square root of pi over 2 gives me 0.48. I should be more accurate. 0.4817. 4 decimal places, please. And then if I do sneak a negative in there, I would have 2.66. I'm going to round it anyways. Maybe 660s. But yeah, we'll just do 2.66. Do I want both of those values? No. Well, I only want one of them. Which one do I want? 0.48. Why, Max? That's in our interval, right? The other one is not in our interval, 2.66. So that's good. Okay. All right, questions there? All right, one more. Okay, 2 cyclists begin a race at 8 a.m. They both finish the race 2 hours and 15 minutes later. Prove that at some point during the race, the cyclists are traveling at the same velocity. Nice little proof. If we're doing velocity, what are we looking at? Like, what would I use to get to velocity, just in general? The derivative, right? So the rate of change in my position function, which I don't have, I need to show that their velocities are the same, okay? We could talk about, like, position function, though. So let's talk about, like, cyclist 1. Their position function, let's say, is, let's just say that's f of t. All right? And then cyclist 2, let's say their position function is g of t. What I want to prove is I want to prove at some point f prime of t is equal to g prime of t on our interval. What is our interval, by the way? Let's say we do it in terms of hours. Max, what's going on in your brain right now?
0 to 2.25.
Yeah, okay. 0 to 2.25 or 9/4 if you want to. But that's our interval that we're working on, okay? T is an element of this. First of all, is my function continuous? Like, is there a constant position for these cyclists? There are, right? Is it differentiable? Do they have a rate of change at every point? They do. Okay. So at some point, I want to prove that these two are the same. Now, here's what you can do. We can think about this instead of like just their independent positions. We could think about it as the distance between the two positions. Because what do you know about the distance at the starting time? It's 0. It's 0. What about the finish line? 0. Doesn't it say they both cross at the same time? They both finish 2 hours and 15 minutes later. So that means your position is 0, or the position, the distance between the two is 0 at both your endpoints. So we could say this, we could define a new function h of t being f of t minus g of t. And that is the distance, or the difference in their distances, okay? And we know that h of 0 equals 0, and we know that h of 2.25 equals 0. So it kind of seems like, what theorem are we trying to use here? Rolle's theorem, right? Because we know the outputs of our endpoints are at 0, okay? Well, is it continuous? Yep. Is it differentiable? Is h of t differentiable? And our endpoints agree. So then what would Rolle's theorem tell me? At some point in that interval, there'd be a value c such that h prime of t is equal to 0, okay? So I could say by Rolle's theorem, there must be some point c, element of 0 to 2.25, such that h prime of t is equal to 0. But let's talk about why that's important. Because h prime of t would be equal to, like if I look at what h of t was, that'd be equal to f prime of t minus g prime of t, right? And if that equals 0, then what can I get from that? That they're equal. Then f prime of t equals g prime of t. I should say this. Let me change a couple things, I'm sorry. Instead of, like in the sentence that I wrote up above, instead of saying h prime of t, I should say h prime of c, is what I should say. Because that's what Rolle's theorem says. It's a specific point, okay? So then, by virtue of that, I should change these t's as well too, and then that'll get me what I want. I don't necessarily know that those derivatives are equal to each other everywhere. I just know that there has to be a value c such that those values are equal. So therefore, f prime of c equals g prime of c. All right, questions there? Okay, I thought this one would be a nice way to round out the week. It's a pretty simple section. This next group of sections that I will teach you, I can't remember what it is. I think this was 4-7. So I think it's like 4-6, 4-7, 4-8, and then 3-8 and 3-9. I think I do those 5 sections together, and then we will assess over those before moving into chapter 5 stuff. Okay? It's a bunch of like random applications of derivatives. All right, if you want more time on your test, grab your calculator. Your homework is attached here, by the way. It's the correct homework assignment.